Thank you for the introduction. So this is joint work with Argyrios Deligkas from Royal Holloway, John Fearnley from the University of Liverpool, and Alexandros Hollender from Oxford. Okay, so this is constant approximability for Fisher markets. So let me just introduce what a Fisher market, let's say what Fisher market is. I'll move this also. Okay, Fisher markets. So they are places where goods are traded, and the typical transaction in such a market is the following. Suppose we have some goods, let's say apples and oranges, and each of them has some particular total available amount. Here it's 1 kilogram, and each of them has a price. Here, $16 per kilo and $10 per kilo. And then the buyer appears that has a budget, and suppose that she desires to buy 50% of apples and 70% of oranges. Then she just pays the right amount and gets the corresponding units of her good, and now she has a bit less of her budget, and the remaining good for the rest of the buyers is also less, right? Okay, so let's make things a bit more formal. You have many goods, many buyers, and each buyer is interested in some good, right? So you have the squares being the buyers being interested in goods, and this is represented by an arrow. Okay. And we have utility functions here. One utility function per buyer towards a good. So we will have some specific utility functions which are called additively separable piecewise linear concave functions. Okay, you can see why piecewise linear because they look like this, and concave because they go like that with diminishing returns, basically. Additively separable means that the total utility for each buyer is the sum of the individual utilities for all the goods. So let's just do a very simple example to digest this. So let's suppose that we are focusing on this buyer and the goods that he's interested in. And suppose that these are the utility functions, one for each good. Then the total utility is this, given that he wants to buy 0.2 from this good and 0.3 from that good. Right? So it's the sum. Quite simple. And additionally, each of the buyers has a budget for buying the goods, right? So this is what we are given in the market. We are given the utility functions of the buyers for the goods and the budget. Now, well, we desire market equilibrium, and what is the market equilibrium in this setting? It's a magical set of prices, one for each good, and a set of allocations. All right, so what portion of each good will go to what buyer, such that first every buyer gets an optimal bundle xi. Okay, so it tries to maximize her utility. Okay, and this is subject to respecting her budget. Okay, so Pj xij is the amount that it gives in order to buy xij amount of good to j, and so the total amount that he gives is this sum. Therefore, he has to respect this inequality. Right? Okay. So this is an optimization problem that we give to the buyer given some prices, and for this SPLC function that I just mentioned is just an LP that he can solve in polynomial time. So this is not a hard task to do, but besides that, he can also follow a greedy method by which he will have to order his goods according to the bank for the buck measure, which is the slope of the utility function over the price, and then greedily buy the goods until his budget is over. Okay. So I'll not do this very simple example, just for the interest of time. All right, let's skip these and find the one where it starts. All right, so we saw what an optimal bundle is. The second condition we have to respect is the market clearing condition. So the market has to epsilon clear. What does that mean? It means that so 100%, almost 100% of each good will be bought in an equilibrium. And here, without loss of generality, we have assumed that there is one unit of each good. Okay, we can do that. The total demand for a particular good is this sum of xij's overall buyers. And now what we want is that the demand does not exceed the supply by epsilon, and it is not smaller also than epsilon. Okay. So that's a very nice set of conditions that we would like to have. Seems like a perfect thing to have, and well, it turns out that this thing always exists also, as long as this sufficient condition is satisfied. So for each buyer in the market, there is one good, at least one good, such that the utility of the buyer for that good is strictly invisible. Okay. So the buyer is never situated, basically. That's what it means. And the equilibrium exists even for epsilon equals 0. Okay. But since we are in the equilibrium computation session, this is not enough. So we want to actually compute an equilibrium like this. And so the question here is, how fast can we compute an equilibrium? Right? So a lot of work has been done on this front, and mainly on polynomial time algorithms. People have been searching for them. And they have come up with some very nice algorithms, even for exact equilibria. But it's only for a restricted family of utility functions. So, for example, for linear functions, or homogeneous functions, or weak gross substitutes functions. And if you go beyond these simple utility functions and you go to PLC, for example, then you have to have constant number of goods in order to have a polynomial time algorithm. Or you have to have a constant number of buyers. And then you get a fixed parameter approximation scheme. So as long as you go beyond this type of either simple utility functions or some constant buyer good number, then you have immediately PPAD hardness, even for very, very simple utility functions, just like the ones I described. And this is for epsilon inverse polynomial in the input size. All right. And this was by Chen Teng and Vazidan and Yanakakis in two papers that independently came out almost at the same time. Right. So the thing is this now. We know how to get an epsilon equal 1 approximation, because if you put all of the items to have price, infinite, and then no buyer can demand more than an infinitesimal amount of it, then you get an epsilon equals 1 approximation. So what we're interested in is something between 1 over poly and 1. Okay, so there's this gap here in the literature. So we push this frontier from the inapproximability side. So we showed that it is actually PPAD complete to compute an epsilon approximate market equilibrium in Fisher markets with these simple utility functions for any constant epsilon smaller than 1 over 11. Okay. So in simple words, what this means is that unless the whole class of PPAD can be solved in polynomial time, there is no polynomial time algorithm to find an approximate equilibrium where all goods clear up to within 9% of the total supply. And 9% seems to me like a pretty big number. So it's it actually says that you cannot do much in reality. So also, we cannot hope for a p-test because there is this constant inapproximability. Additionally, by doing a reduction from Fisher markets to the other group, exchange markets, and keeping the same epsilon, we can actually get the same inapproximability for these kinds of markets, which are a more general setting, right? And the state of the art by the time was that there was a known inapproximability for a very, very small epsilon, which came from Rubinstein back in 2018, but this was an unspecified, very small constant. So for any practical reasons, this would still leave open the case of an approximation algorithm, even for 0.001 approximation. Okay, so I have assumed so far that everyone knows what PPAD is and why we don't like PPAD hardness for our problems, but just to be sure that everyone follows a bit, PPAD is a complexity class that stands between P and F and P, and it includes many interesting problems like computing Nash equilibrium in games, or Brouwer fixed points, or solutions to k-cutting, equilibrium functional networks, and many, many more interesting problems. So it is conjectured that just like NP, PPAD does not equal to P. Okay. So we don't have even sub-exponential algorithms for PPAD hard problems. Okay, so let me say now a few things about the reduction itself. So we're going to show PPAD hardness, right? So we are starting from the simplest PPAD complete problem that is currently available, which is pure circuit, and this was defined by a prior paper of ours back in 2022, and the input of this problem is a Boolean circuit, which is a bit weirder, actually. So it's a circuit that has cycles, and instead of its values getting only, so instead of its values being only 0 and 1, it also takes a garbage value, this one here. Okay. You can think of it as some value between 0 and 1. And also, on top of the standard logical gates of a Boolean circuit, it can also have something called a purified gate. Now, the task is to assign a value in 0, 1, or garbage to each node such that the gates are satisfied. Right. So here is how the gates look like. We are using the version of the problem that is the simplest possible, uses a NOT gate, a NAND gate, and a purified gate. And these are the truth tables of these gates. So what I want you to keep in mind, okay, don't read all of this, of course. Just remember that for pure bits, whenever you have a 0 and a 1, the gates are as usual. And when there is garbage in the input, then something weirder happens in the output. Let's focus here on the purified gate also to see what it does. It has a single input, but 2 outputs. So whenever you have a pure bit, it just duplicates it. When you have a garbage input, then it outputs at least 1 pure bit. That's it. So that's why it's a very, very simple problem. And that's why we start from there. Okay, so going from Fisher markets to, going from pure circuit to Fisher markets, we are creating gadgets that simulate the gates. So this is how a node gadget looks like, for example. So we take each of the nodes of the circuit and we make one good representing that that node, right? So you have the input good, you have the output good, and then we create a buyer that is called an inverter that is interested in both these goods, and also is interested in one big good. Okay, it's a very valuable good that's called the reference good. Right. And there are some auxiliary buyers as well that like the output good and the reference good. Yeah. But the reference good actually is one big good that everyone likes, and it's there for technical purposes. Okay, it doesn't play any other role. So you just focus on these little goods here. Okay, and the NAND gate looks like this. So it's basically a generalization of the NOT gadget. It has these two input goods and one output good. And the Purify gadget now uses many NOT gates in a chain, starts from an input U and has two chains of NOT gates that lead you to V and W. Right? And of course, everyone is interested in the reference good. I will not go into details about the correctness of the gadgets, but I'll just show you how the decoding happens. So we have made a Fisher market out of a pure circuit by simulating its gates. So then we want to go from a solution of the market to a solution of pure circuit. So this is how the decoding happens. Suppose that you have these NAND gates and you have a good here, let's say U, and we take the price of the good and we look at it in an equilibrium. And there is this scale. The top is the reference goods price, and there is a high value and a low value for the price, and then it's zero price, of course. And depending on what the price of U is, we decode it as the value of the node. Okay, so if it's at least H, then it's N1. If it's at most L, then it's a 0. And if it's anything in between, it's a garbage value. And so this is how it looks like. And so that to give you a picture of how the instances look like, how complicated they are. Suppose that you start from a very simple instance of a pure circuit. This is the market, the corresponding market from the reduction. So you can see that it's not crazy, difficult or complex, right? So even these simple instances are PPAD hard, basically. Okay, just to summarize, unless there is a collapse of PPAD into P, we cannot hope to find an epsilon approximate equilibrium in a Fisher market with separable piecewise linear concave utilities for any epsilon that big. And this holds even for these simple market instances that I just showed you. And the same inapproximability transfers to our exchange markets. Now, the open problems are, of course, related to closing this gap that exists, the new gap between 1/11 and 1. So can we close this gap from below? Can we find some better hardness, some larger inapproximability? Or can we find some polynomial time algorithm for some epsilon that is at least 1/11? If we cannot do that, well, can we at least find such a polynomial time algorithm for the specific instances that we have, which have degrees at most 4, except for one good that is the reference good. Yeah, so that's all. I'll be happy to answer your questions. Thanks.